You can just draw a circle inside the ring if you can't get the double bonds in there.
Okay.
All right, cool. All right, we'll take it. Anybody disagree? You have your aromatic ring here and the bromine attached. And you know you can write that aromatic ring with a circle inside. It's called a calculate structure. Uh, and it just means that those electrons in the ring are always in resonance with one another. Sorry. All right. Any questions about that problem? Hey, what about the next problem? And what type of reaction is it?
Would that be a Friedel-Crafts alkylation?
It is. It's alkylation. Good. And that means I'm adding an alkyl group to the ring. Is that right? Alkyl, just all carbons, no double bonds, no, you know, all carbon, hydrogen, single bond. So I'm adding an alkyl group. All right. Where on the alkyl group is the ring going to attack? Anybody? So you have an alkyl halide. Where's the ring going to attack?
Oh, the ring attacking the tertiary carbon.
Right here, right? That's the carbon that's going to get attacked. So somebody hit your annotate button and draw that product. The ring is going to be untouched. Okay. Perfect. That's exactly right. So the product is going to look like this. You have your ring, and boom, it's going to attack that tertiary carbon. So now the thing asks you to propose a mechanism for 3, right? So I'm gonna give you about let's say 5 minutes. Let me see what song I can pick today. Let me go to my playlist. I know I'm old, so I ain't got nothing but old stuff. Let me see. got something decent. There we go. All right. Of course, you got to guess the song too. So 5 minutes. I'm gonna pause the recording, and then we'll come back. Let me start the recording back. Let me see if I can let you share your screen. Where is it? All right, try clicking on the. I think it's one of the buttons on the toolbar. It will let you share your screen. You can show us what you did, and then of course.
You cannot share screen. Start screen share while the other participant is sharing.
Oh, okay. All right, try it now.
I can show my video. I'll do the video. Can you see me?
Yeah.
Okay, it's kind of dark in here, actually.
Start back recording, and then we're gonna. You had the right idea in the first step. The only problem was that you kind of merged 2 steps instead of separating. So for the electrophile to be prepared, you're going to take the electrophile here, and then here. And then that, of course, that's going to form a complex with iron chloride. Is that right?
Mm-hmm.
And then because it's tertiary, you're probably going to lose that chlorine and make a tertiary carbocation plus FeCl4 minus. All right. And so that's the first step, the electrophile preparation. And then in the second step, that's when your ring is going to come in. So this is, I'm gonna label this step 1. And step 2 is where the ring is now going to, let me change those double bonds around. So that carbocation now is going to get attacked by the ring. And I think in the first step, you kind of merge these 2 steps together.
I do.
Yeah, but you have to separate them because you have to show first the electrophile getting prepared, and then the ring attacking the electrophile and giving you this uranium intermediate. I think you had that part right too. Let's see. So the plus charge is going to be here, and then now I'm here.
Mm-hmm.
Right? And so now, step 3. Rearomatization. All right, so I'm gonna take that intermediate that I made in step 2, the uranium ion, and I'm gonna do elimination with FeCl4. So now I'm gonna take that, boom, pull off that proton, give those electrons back here to make a pi bond, and it's gonna give me my product. So the aromatic ring here, plus catalyst regenerated, plus HCl. All right. So it's always those 3 steps. First step is the preparation of the electrophile. Second step is the attack of the ring on the electrophile. And then the third step is re-aromatization of the ring. Oh, who can guess the song that was playing? And the group.
It was Cool by Prince.
Ah, close.
The
Very
time.
close. By the time.
The time.
Yeah. Same.
Oh, the band.
Yeah, but Prince kind of made them, so you're very close. So make sure you include that. I'm gonna make this mechanism an extra credit, and I'll post it up today. So make sure if you didn't finish it, you should be able to finish it, and then make sure you include the song that we heard while we were doing it. Yeah, but Prince kind of made it was his band, and he played all the instruments on the album, just not when they played live.
Oh yeah, okay.
Yeah, he really like made them. All right. Okay. Here's another question here, and then we'll finish this, and then we'll probably just stop for the day and pick it back up on Friday, dealing with mass spec. So it says a Frito craft is carried out on a primary alkyl halide. Sometimes unexpected products or form propose a mechanism for the reaction below. All right. So we kind of did this Monday, but I fixed that example because the example we did Monday was a little bit different. And I actually had an error in there that I went back and corrected in the notes, even though it wasn't corrected on the video. So let's see what happens here. What's the first step in this mechanism?
Prepare the electrophile.
An electrophile. Nothing changes. So I'm gonna prepare my electrophile by taking this and reacting it with FeBr3. Let me just show the complexation part. So this is gonna complex here, right? And then I'm gonna go ahead and show the carbocation so we can show what happens to it. So when that comes off, we're left with this carbocation. Is that right? Where this carbon right here is now here. Plus iron tetrabromide. All right, now, so for the carbocation, let me see if I can cut it and move it. What's going to happen to that carbocation? Let's look at the product. It doesn't look like in the product that the ring attacked that primary carbon because this is the same carbon down here. Are you following that?
Yeah.
Yeah.
So when we talked on Monday, we talked about these carbocations being able to rearrange. And so you could do a hydride shift. In this case, it'll be a 1,3 hydride shift, right? Because you're not going to pull off a hydride from this carbon. That would be a 1,2 shift. It's going to come from here, so you can make that tertiary carbocation. So I'm going to show that in a different color. Right, so this is coming all the way here to this carbon, right? And so now your cation is going to look like this. Right, that becomes it's a CH2 on this side. It becomes a CH3 after the shift. And then now this is my cation. All right. And then that now goes into the second step. I don't know what they're doing, but it's loud. Now what?
Now the ring attacks that carbocation.
Right. This is the mechanism. Really, it doesn't change once you get past that first step. You're going to attack the carbocation here, make the rhenium ion, like so. Let me fix that up. Right, and then after that, it's the same thing. You get re-aromatization. So the intermediate from here right, that intermediate is now going to react with the leftover, well, not leftover, but the iron tetrabromide, and then you'll get a proton transfer, elimination, and then that'll give you your product. And then HBr plus FeBr3, right? You always regenerate your catalyst so you can go back and do another turnover. Once you get to the product, the iron bromide can go back and start catalyzing another reaction. All right. Any questions about that? All right, let me add another piece into here, and then we're going to stop. So I want to do all right, let's take that product. What would I get from that if I took that, the product that I just made, and I brominated it?
Didn't you say like since it's a halogen, it will go to? No, never mind.
Here, the BR.
Okay, I'm adding a halogen, but what do I have to think about now since the ring is substituted?
If it's a donor or
Whether
acceptor.
donor is separate.
Yes. So is an alkyl substituent on an aromatic ring, a donor or an acceptor?
Donor.
It's a donor. Good. Right? If it's a donor, then it's going to be ortho and para directed. So where is the bromine going to attack, or where is the bromine going to end up in the product? How many products should I expect?
2.
Okay, I heard somebody say 2.
Question: how do you know what's a donor and an acceptor?
Okay, so I gave a list, but it's like alkyl groups or donors, heteroatoms like nitrogen, oxygen, sulfur, uh, anything that can donate either a pair of electrons into the ring or can donate electron density through induction. There's a list somewhere in these notes. Oh no, I take that back. It's in the other handout that I have uploaded to Blackboard.
Okay.
But all alkyl groups are donors. And by donor, I mean donating electrons. All right. So a donor is going to be an ortho-para director. And so when I brominate, this compound, I should have a bromine here. And I should get a bromine here. All right, this is 1, 2, or ortho. And when I say 1, 2, it's in relation to the group that's already attached, the substituent that's already on there. And then this is 1, 4, but we don't use numbers for di-substituted aromatic rings. We use ortho, meta, or para. Right, so if you have a donor, it's going to be ortho or para. You're going to get both products. And which one do you think is going to predominate? Which one is going to be major?
Para.
Para, right?
Yeah.
Because of sterics, right?
Mm-hmm.
All right. We can squeeze in one more. Then we'll stop for real. What if I took the product from this reaction and I alkylated it? What do you think? What when I have a substituent on the ring, what do I have to start thinking about?
What is donor receptor?
Yeah, anytime you got a substituent on the aromatic ring, you have to start thinking about directing effects, whether it's a donor or an acceptor. All right, so this is, you have actually have a carbonyl on the ring. What do you think, donor or acceptor?
Acceptor.
Yeah. All carbonyls are acceptors. Right, all carbonyls are acceptors. So if you have an acceptor on the ring And this is for electrophilic aromatic substitution, right? It is morning time, right? That's how I like to think about it. An acceptor is going to be a meta director. So morning time, AM. That's a good way to remember that. All right. All right. So if the acceptor is on the ring and it's a meta, where is the meta position relative to the acceptor?
1, 3.
Good. Right. It's right here. Because the meta position is the 3 position relative to the substituent. So this is 1, that's 2, and that's 3. But because it's because we're forming a dye-substituted aromatic ring, we don't use numbers, right? We use the ortho-meta para convention. So this is the product. That stays the same. And then we have, where did I put? Oh, it's a tertiary, never mind. Then we have the tertiary alkyl halide, which gets added here. Plus AlCl3 plus HCl. All right, any questions about that? And then again, this is at the meta position. All right, any questions about that? All right, if there's no questions, we're gonna stop a little early today. I'm gonna go ahead and upload, or not upload, yeah, I'll upload the notes, the video, but I'm gonna upload a link